Greetings, hello, welcome. Let's sketch some more rational functions. Let's say you're given a rational function x squared plus x, x squared plus x minus 2 divided by x squared. So they are all quadratic equations. Minus 6 minus x minus 6. Yes. And your friend asks you to sketch, or maybe you're asked to sketch this in a test by your teacher. Before sketching this, we need to attempt to factorize. So before you sketch it, just factorize, see if you can write it in its simplest form. Factor out if you can factor. If you need to use the quadratic equation to do it, it's still fine. So in this case, look for a number. Okay, I'll just write that like that. Now look for two numbers, which when I add those numbers, I get coefficient here, which is 1, coefficient of x, and if I multiply them, they give me minus 2. So this will be plus 2 and minus 1. Positive 2 multiplied by minus 1 gives me minus 1, gives me this one. And positive 2 plus minus 1 gives me positive 1, so that's okay. Do the same story here. Write my brackets. And now look for numbers that when I multiply them, they give me minus 6. When I add them, they give me minus 1, coefficient of x. In this case, numbers will be minus 3 plus 2 gives me minus 1. Okay, so plus 2. Alright, right here we can see that we can factor this one out. This one and this one cancel each other out, and this simplifies to x minus 1 divided by x minus 3, which is cool. Alright, nice. So if we want to plot this, if we are asked to sketch this, we will find our vertical asymptotes. That's the first thing we do. Find our vertical asymptotes. And the vertical asymptotes are located where? At the zeros of the denominator, which is what? X minus 3 equals to 0, therefore our 0 is x is equals to 3. Okay, so vertical asymptote is located at x is equals to 3. But what about this one? X plus 2. X plus 2. If we were to take that whole thing as our denominator, x plus 2 would give us x is equals to minus 2. So this is also a 0 of that denominator. It's a 0. But then since this one was cancelled out, this one is a 0, but then it does not give us the vertical asymptote of our function, but however it does give us what is known as a whole. So whole is located at minus 2, but then we need to find what is our x value for the whole. So let's use this equation to find our x value for the whole. It's going to be minus 2 minus 1 to minus 3. So that will be minus 3 divided by minus 5. So we have a whole located as 3 over 5, which is what? 3 over 5. 3 over 5 is the same thing as 0.30 divided by 5. That is 6. So 0.6 over 5. So there's a hole at minus 2 and at 0.6. That's the coordinate of the hole. Cool. Let's find the horizontal asymptote. Horizontal asymptote is found where we look at the order of the polynomials, the numerator and the denominator. They are all of the same order. Therefore, we divide the coefficient of the highest of the variables with the highest order. In this case, is 1 over 1. So, located at y is equals to 1. X-intercept is found when y is 0. So 0 is equals to x minus 1. Equate the whole equation to 0. 3. So this one multiplied by 0 gives us that x is equal to 1. So at 1 we have the graph intersects the x-axis. Okay, what's a y-intercept? Well, we get a y-intercept by substituting 0 in for every variable of x. So let's do that. F of x is equals to 0 minus 1 divided by 0 minus 3. And then we have minus 1 over minus 3, which is 1 over 3, which is equals to 0.333 recurring. Okay, so 1 over 3. That's our x-intercept. Okay. Now we have our x-intercept, we have our points. Now let's plot our graph. Okay. Okay, this is where I'm just drawing our Cartesian coordinates. Vertical asymptote located at x is equals to 3, and horizontal asymptote at y is equals to 1. Okay, x is equals to 3 and y is equals to 1. Okay. Okay, so let's plot our x-intercept. X-intercept is at when x is 1, x is 0. When x is 1, I say x now. When x is 1, y is 0. So that's that point on the graph. What else? When x is 0, y is 0.3. When x is 0, y is 0.3. Let's put it somewhere here. 1 over 3. Okay. What else? We have a hole. Let's plot the coordinate of the hole. The hole is at -2, at -2. -2, 0.6. Let's say this is 0.6. So there's a hole there. Okay, cool. So already from here we can see the graph is in this region. Our graph is found in this region, goes all the way, intersect the y and intersect the x. So there's our graph. And then it has a hole. So there's our graph in this region. Here we can already see it should be in this region, but let's make sure. So to make sure, we substitute points. Let's substitute 4 in our equation and see what value of x we get. F of x is equals to 4 minus 1 over 4 minus 3. It's x minus 1, x minus 3. So 4 minus 1 is 3. 4 minus 3 is 1. So when x is 4, y is 3. And let's plot that point and see where it's found. Okay, this is 1, then 3 will be somewhere there, and here will be our 2. There will be 2, there will be 3. So this tells me our graph is in this region. On this side, graph is still defined in this region. Okay, cool. And it has a hole. Alright, so let's write down our domain. So our domain will be domain for this graph would be, okay, this is all the way from minus infinity, well, there's a hole at -2 that we need to exclude that. Union from -2, well, goes all the way to 3. That's where we have our vertical asymptote that also needs to be excluded. Then from 3 the graph is valid all the way to positive infinity. Cool. So this can also be written as graph is domain is valid for all values of x except for x equals to -2 and x equals to 3. Okay, so at those points the graph is so defined. So alright, cool. So what about the range? How would the range look like? Range would be from minus infinity all the way, look at the graph, all the way, well, 0.6, which is 1 over 3, over 5, 0.6. So that must also come out all the way to 3 over 5. 3 over 5 continues all the way to the horizontal asymptote to 1. It must also come out, then goes all the way from 1 to infinity. So that's our range.